All right, everyone, welcome back to the channel. You guys know we love to talk about some of the more, complicated and nuanced stuff when it comes to electronics.
Oh, yeah, absolutely.
But today, we're going to be talking about something that, everyone who works with electronics has to know. That is, we're going to be talking about electronic components.
The building blocks.
Exactly.
Yeah.
The building blocks of, just about everything, right? Our computers, our phones, our TVs, even a lot of the stuff we use in industrial settings, it all comes down to electronic components. But first, before we dive into the different types of components and how they work, let's talk about something that often gets confused. Electronic components versus electrical elements. What do you think? What's the difference there?
Well, I think it's a great place to start because you're absolutely right. Those terms do get confused quite a bit. I think the simplest way to put it is electronic components are the actual physical things. You can hold them in your hand. You can solder them onto a circuit board. So, we're talking about your resistors, your capacitors, your transistors, diodes, all that good stuff.
Right. They're like the ingredients.
Yeah, exactly. Think of them as the ingredients in your electronics recipe.
I like that, the ingredients. And then the electrical elements, those are more like the theoretical concepts, right?
Exactly. Like resistance, capacitance, inductance. Those are the electrical elements. They're the principles that govern how electricity behaves. And each electronic component is designed to exhibit a specific electrical element or maybe a combination of them.
So it's kind of like the components are the tools and the elements are the jobs those tools do.
Mm-hmm.
Like a hammer is a component and hammering is the element.
Yeah, I think that's a really good way to put it.
Okay, so now that we've got that cleared up, let's talk a little bit more about how to actually use these components. And one of the most important things to understand is the concept of a data sheet.
Yeah, data sheets are essential.
Right, because let's say you're working on a project and you need a specific type of transistor. You go online and you find a bunch of different options. How do you know which one is right for your circuit?
The data sheet, it's really the Bible for that specific component. It tells you everything you need to know. The voltage ratings, the current limits, the operating temperature range, the pinout, all of it. Plus, you usually get performance graphs and characteristic curves that help you visualize how the component behaves under different conditions.
It's kind of like getting the instructions for your ingredients, right?
Exactly. It tells you how to use that ingredient properly. And trust me, you don't want to skip reading the data sheet. Otherwise, you might end up with a circuit that doesn't work. Or worse, you could damage components.
Speaking of circuits, let's talk about how these components actually come together. One of the most common ways is in something called a discrete circuit. What exactly does discrete mean in this context?
Well, in a discrete circuit, each component is separate, individual. They each have their own specific function, and they're connected together with wires or traces on a PCB. Think of it like building a house brick by brick. Each brick is a separate component, and together they form the structure of the house.
Okay, so if a discrete circuit is like building a house brick by brick, what would be the opposite of that?
That would be an integrated circuit, or an IC for short. These are the little microchips that we find in pretty much everything these days. In an IC, you have thousands, millions, or even billions of components like transistors, resistors, and capacitors, all tacked together on a tiny piece of silicon.
Wow, so it's like a whole city built on a single chip.
Exactly.
Yeah.
And they're incredibly complex. Designing and manufacturing ICs is a whole other level of engineering. But the basic idea is the same. You're still using electronic components to create circuits that perform specific functions.
So we've got discrete circuits and integrated circuits. And within those circuits, we've got all these different types of components. We can actually categorize these components into three main groups: active, passive, and electromechanical. Active components, like transistors and amplifiers, they need some kind of external power source to work. They can also amplify or modify electrical signals, which is really important for things like audio amplification or signal processing. Think of it like they need a battery to function, and they can make a weak signal stronger.
And that brings us to passive components. These guys, they're a little more laid back. They don't need any external power to do their thing. Resistors, capacitors, and inductors are good examples. They mainly store or dissipate energy, shaping the flow of electricity in a circuit.
So passive components, they're like the traffic lights of a circuit. They control the flow, but they don't generate any power themselves.
That's a great way to put it. And then we have electromechanical components. These are kind of a hybrid, a mix of electrical and mechanical parts. They involve physical movement in some way. Relays, switches, motors, solenoids, these are all electromechanical.
It's fascinating how we can use electricity to create motion, isn't it?
Yeah, it's really amazing. And all these different types of components, they all work together to create the incredible variety of electronic devices we have today.
And when we're talking about active and passive components, especially from the perspective of circuit analysis, it's important to remember that the definitions get a little more specific. It's not just about whether they need external power or not.
You're right. When we analyze circuits, we're often focused on the AC signal, the part of the electrical signal that's actually carrying information. We tend to ignore the DC power source, kind of like we're zooming in on a specific part of the circuit's operation.
So it's like we're looking at the ripples on a pond, not the pond itself.
Exactly. And in this context, an active component is something that can add energy to the AC signal. So a transistor amplifying a signal is a good example of an active component. A passive component, on the other hand, can't add energy to the signal. It might change the shape of the signal or filter out certain frequencies, but it can't make it stronger.
So if an active component is like someone pushing a swing to make it go higher, a passive component would be more like the air resistance that eventually slows the swing down.
Yeah, I think that's a really clear analogy. And to analyze these passive components, especially those with multiple terminals, we use a tool called two-port parameters.
That sounds a little intimidating.
Don't worry, it's not as scary as it sounds. It's basically a way to describe how a component interacts with signals at its different ports. You have signals going in, signals coming out, and two-port parameters help us model that relationship mathematically.
So it's kind of like a map of the component's behavior.
Yeah, exactly. And one of the key principles that often comes up when working with two-port parameters is the principle of reciprocity. This basically states that the relationship between the input and output signals remains the same, even if you swap the input and output ports.
That's interesting. So it's like a two-way street. No matter which direction the signal is going, the component behaves the same way.
Exactly. It highlights a kind of symmetry in how these components operate, which can simplify things when you're doing circuit analysis.
And to make things even easier, engineers have developed standard symbols to represent each component in circuit diagrams. It's like a universal language that allows engineers all over the world to understand each other's designs.
And that's a powerful thing. It allows for collaboration, innovation, and really rapid progress in the field of electronics.
Well, that was fantastic. I hope this has been helpful for everyone who wants to get a better understanding of the building blocks of our technological world.
Absolutely. And if you have any questions or want to dive deeper into any of these topics, feel free to leave a comment below. We're always happy to help.
As always, remember to like and subscribe to the channel for more great content from us, your AI experts who break down complex topics in electronics.
Until next time.
See you later.